Wow, Mrs. Reinfelder, there seems to be a lot going on this board. What are we talking about this week?
Oh, we're gonna leave dirts and rocks behind for now. I'm a little done with that.
I'm a little done too.
Yeah, and we're gonna go into my favorite thing, physics.
Physics!
Yeah. Physics is all about how objects interact with each other in the universe, and it is one of my favorite topics. And to boil it down a little bit for today's lesson, physics is mostly about forces. And I know a lot of you have seen or heard of Star Wars and you're like, oh, the force be with you, and you think, oh, that's all made up stuff. And it is and it isn't. It's a little bit real physics because in Star Wars, they use the force to push things away or to pull things towards them. And that is actually what force does.
There are a couple of forces that we have to talk about when it comes to physics. And you guys actually know a lot about these forces. I just have to kind of show you that you know. The first force that I want to talk about is a force that holds us down all the time. It works on us from the minute we're born until the end of our lives, and it's always here, and that force is... That's right, it's gravity. Gravity is one of the 4 forces of physics, and it's always pulling us down to the earth, or it pulls smaller objects towards larger objects.
So Mr. Kyle, does that mean that no matter how hard I jump, I will never be able to just shoot up into the air?
Not with just your legs, no.
Oh, I've been working at that.
You could do it up and away, Miss Reinfelder.
I guess I'm no superhero.
Wah, wah. Another force is magnetism, and the way that we know a force is working is when it moves something, and we can definitely use magnets to move at least other magnets and some other metal material. I can use the red side of this magnet to the blue side of this magnet, and what are they going to do? Attract. They're going to stick together. I didn't push this magnet at all. There was a magnetic force that pulls the magnets together, and I can do it in the opposite direction. I can use a pushing force if I use both blue sides to repel. Magnetism. It's a force.
Wow.
Oh, I'm no Jedi. I can't use the force. So I can't move this bunny unless I touch it, unless I use the muscles in my body to impart a force, but a gentle one, onto Mittens over here. Push it. Whoa! How was that? You want to go again? Force push. Yeah.
So, way back when, in the 1600s, there was a master Jedi of physics. Well, he was at least the master of physics, Sir Isaac Newton. And when he was only 23 years old, he developed a set of laws that govern the pushing and pulling of forces in physics. The first law is if an object is in motion, like a rolling ball, it is going to stay in motion unless stopped by an outside force. What outside force did I just use? You're right, I used my hand to stop that force. Now, that means that if I had a baseball and I threw it as hard as I can, it would keep going forever. But is that what happens on the Earth? On the Earth, there's another force that eventually pulls that baseball down towards the ground. And what force is that? We just talked about it. That's right, it's gravity. Not only that, but the baseball is going to encounter all those air molecules. And you remember when we waved our hand in the air and we could feel the air molecules pushing back against our hand, kind of like wind? Well, the baseball is going to encounter those same molecules, and they will eventually slow that baseball down and allow gravity to pull it to the earth. But if it were in outer space, that baseball would continue going forever and ever and ever and ever, unless it was pulled into orbit of another planet or hit an asteroid or an astronaut got it in outer space. But that would be astronomical. The second part of that law written by Sir Isaac Newton is that an object at resting, is going to stay at rest forever unless acted on by an outside force. What forces could we use to move this golf ball? I can think of three pretty easily. I could move it with my muscles by pushing it. I could also move it with my breath. Or I could squirt it with a hose and put it off the table. But if I do not apply a force to this golf ball will sit in this exact same spot forever. Sir Isaac Newton's second law says that force equals mass times acceleration. Got it? I knew you would. No? You want a little more explanation than that? Okay. Well, let's first talk about mass. What is mass? Now, it has kind of a complicated description. It's more about the density of an object and how hard it is to change the path of that object. But for elementary school and the purposes of talking about here on Earth with gravity, we're going to say it's kind of similar to weight. For example, if I have a golf ball and a ping pong ball, the golf ball has more weight and the ping pong ball is very, very light. And if I drop them both at the same time, which one do you think will bounce back with more force? The heavier one or the lighter one? Take a moment to make your hypothesis. Let's test your hypothesis. I'm going to drop them both at the same time, golf ball, ping pong ball. Let's see what happens. Woo! The golf ball bounced this much higher. Why? Because it has more mass. There's a few other things working there, but for our purposes, we can say the heavier one is going to have more force. More mass equals more force. The second portion of this is acceleration, and you might not be familiar with that word. Acceleration is how fast something is getting faster. And you may have felt this when you were sitting in the car at a stoplight. You're totally stopped, and the light turns green, and the car starts moving forward, and you feel the force that initially makes you rock back a little bit. That is the car accelerating. It's coming up to speed. And so acceleration, for our purposes, we're going to say how fast something is. And this one's pretty easy to explain. If I took this little light ping pong ball and I threw it right at you, it doesn't hurt all that much because it's not going very fast and it doesn't weigh very much. If I threw a chair, which is much more massive, right at you, that would hurt quite a bit. Why? It has more mass. For acceleration, if I got the tennis ball and I throw it at you slowly, it doesn't hurt that much. But if I wound up and really whipped it right at your chest, it would leave a really good bruise because we accelerated it or we sped it up. So the heavier something is, or the faster it's going, the more force it's going to have.
Wow, Miss Reinfelder, you really got excited about throwing stuff at me.
I like throwing things at you.
Sir Isaac Newton's third law is for every action there is an equal and opposite reaction. And this is something you guys understand all the time. Like when you give your friend a high five, if you high five hard enough, it hurts both of your hands, not just the hand being hit. Or if I hit the table, it also hits my hand back. Does that make sense? Another good way of showing this is if I take this ball that's attached to a rubber band and I pull it to the, what is that? Your right? If I pull it to the right and I let it go, what direction is it gonna move in? That's right, the opposite direction. Pew! Ow, I hit my fingers.
One of my favorite forces is spinning forces. And one of the spinning forces is centripetal force. If we use the same ball on a rubber band that Mr. Kyle had, and I hold it at one end, I can change the direction the ball is going. Because normally, if you throw a ball, it's going to go in a straight line. You cannot throw a ball in a circle no matter how hard you try. I actually challenge you to find a ball around the house and see if you can throw it so that it goes in a circle. You'll probably find that you can't. But if we put a ball on a string, especially an elastic string, and we start moving it in a circle, one thing you'll notice immediately is that the rubber string got longer. And that is because that ball is trying to continue in a straight line. And the string that my hand is holding it with prevents it from flying off in a straight line. It forces it to stay in the circle. That forcing it to stay in a circle is called centripetal force. And the force is being provided by my hand on the string. That's what's holding it from flying off into space. This is where Newton's second law comes into play. If I have a very light ball pit party ball and a substantially heavier tennis ball, both on elastic strings of the same length, you will notice that the one that has less mass stays pretty close to me when I spin it in a circle, because with less mass, it's not pulling as hard and it doesn't have as much force. Now the tennis ball, if I swing it with the same amount of muscular action, you'll notice that it's a much bigger circle, and that's because the mass of the tennis ball is putting a lot more force on the rubber band. So it's increasing what we call centripetal force, or the spinning force. Also, you'll see if I spin the ball slowly, the elastic stays short or long. That's right, pretty short. But if I accelerate it, with Newton's second law, it says force equals mass times acceleration, and as I add acceleration, we added to the force pulling on the rubber band, so we increased the centripetal force. You may have felt the effects of centripetal force when riding in the car with your parents. If your parents take a corner really fast, you'll notice that the car has to struggle. It has to have a force that holds it to the road. Thankfully, our tires do this for us, and they hold that centripetal force for us. But if the tires stop holding your car to the road and the car starts to drift, that is inertia overcoming the centripetal force. However, your body experiences something different. You probably feel like you're being pressed against the car door, and that car door catching you and preventing you from continuing in a straight line is another interesting physics concept called centrifugal force, which isn't really a force, it's just a sensation you feel when centripetal force is applied to your body and prevents the inertia of your body from continuing in a straight line.
Now, some of you parents out there may know this, and some of you kids might be a little too young, but we used to have these merry-go-rounds on the playground, which were super fun, but are kind of like being removed because they said they were dangerous and a lot of children hurt themselves or whatever. But I guess I know I fell off a bunch of them as a kid, which probably explains some
It
things.
does explain a few things.
Anyways, when you have this merry-go-round spinning really fast because all your friends were spinning it and you were sitting on it, your hands holding you to the merry-go-round is your centripetal force. That's what's holding you on to the merry-go-round, and you will feel yourself trying to be thrown off. And that's the centrifugal force, which isn't a force. It's just once centrifugal force gets strong enough to rip you away from the merry-go-round, that's just inertia overcoming centripetal force. So centrifugal, not a force.
Centripetal force and the resulting sensation of centrifugal force is something that we experience all the time when we're doing carnival rides. I know that when I was little, I was really afraid to go on rides that went upside down, and I was sure I was going to fall to my grisly death. But if I had understood more about the forces of physics, I would have understood that due to centripetal and centrifugal forces, that's an impossibility. I'll prove it to you. So pretend that this cup is our carnival ride passenger, and it's filled with squishy water, just like you are, very delicate. And I put this cup in my carnival ride. Now, I can make this cup go upside down without spilling an ounce of water. Let's check it out. Woo! And if we slow it down and return it to the table, Mr. Kyle, can you check that there's no water in the tray? No lid on the glass, no glue on the cup. And you can see that the centripetal force of the string and the resulting centrifugal force keeping inertia from making my cup go in a straight line forced the water down into its cup, even when it was upside down. And you can try this with water in a bucket outside, see how it works for you. But you know, scientists, once one thing works, they always want to see how much further they can push it. Push it. Yes, let's try 2 glasses of water. Cause, I don't know about you, but I like to ride on my carnival rides with a friend. And that adds mass, so is it going to change our outcome? Let's find out. Woo! Ah! Perfecto! Mr. Kyle, any water?
Looks dry to me.
All right. Well, like I said, scientists like to push the limits, so if 2 cups worked out, what about 4 cups?
Oh no.
Yes, let's do it, do it, do it, do it. Okay. All right, we got 4. Let's try it out. I'm a little nervous, Mr. Kyle. Woo! Ah, just a little bit of water. I tested my luck too far. Well, that's the point that a scientist says, ha, that didn't go well, and I must try it again a different way. Science! Isn't failing wonderful?
A couple of fun things you guys can try at home is putting some water in a bucket and taking it outside with your parents' permission and swinging it over your head to see if you can get that water to stay in the bucket. Another thing I like to do is to take a marble and put it in that bucket and then spin the bucket and see if I can get the marble to climb the walls of the bucket and see how long I can get it to stay there also. And another thing is I like to take a balloon and put a little nut inside of it.
You know, like nuts and bolts.
Like nuts and bolts. And then you can spin it and see if you can get it to climb the walls of the balloon. Let's listen. Nope. Yeah.
It also makes a cool sound.
That's nice and obnoxious. Now, if you guys try this stuff, it would be great if you made a short video or took a picture and shared it with us. Or you could just leave a comment and tell us how it went for you. You know, Mrs. Reinfelder, one of my favorite things about physics is there are examples all over the place, all over our world of how cool they are and how it works.
All the forces at action on every object at all times. It's really cool.
It is amazing.
May the force be with you.
This is the way.